Well, thank you. Welcome all of you. Hello to the people who are here. Hello to the people who will be watching that online. Hello to the cameraman. I am going to talk about quantum gravity. To talk about quantum gravity, I will break this in 4 parts. The first, I will talk about gravity. Second about quantum, and the third about quantum gravity. Right? In the first and the second, I will just very rapidly review what we know about gravity and about quantum in a way which I think is, sorry, I need drugs to work. It's caffeine. In a way which is adapted to put them together. And then in the fourth part, white holes, I will address the key problem in quantum gravity, which is to find experimental evidence that what we do is correct or not correct. We, in quantum gravity, have a problem, which is bringing what we know about space-time, what we know about quantum theory together, so do the quantum theory of space-time. We know that space-time has quantum property, or we strongly believe that space-time has quantum properties. We have tentative theories for describing quantum space-time. It's nice, beautiful. Some of us are passionate for one theory. Some of us are passionate for another theory. The problem is to know whether these theories are correct or not. And to know that, we have to make measurements and confirm or disconfirm, support, or find evidence for or against the theory. And that's the most interesting part of the game, I think, because after all the conceptual work of figuring out what is quantum space-time, we have to come back to reality and check these ideas against reality. And I will talk in the last part about one recent idea of how to check our understanding of quantum gravity using white holes. So 4 chapters. First chapter, gravity. Gravity, of course, is what makes things fall. That's the name of gravity. And the way we have understood gravity for a long time is, of course, through Newton theory. And Newton theory is Newton had the idea of understanding gravity in the following way. First of all, there is some space. And let me make you, this is my model of space. In space, there are the moon, the sun, the objects that move. And the idea of Newton is that there are forces, right, as you all know, between any 2 objects, between the sun and the earth, between the moon and the earth, between the earth and this thing which is falling. So things move in space straight. Space is like a huge container of everything. It's a very Newtonian idea, space. Things move straight in this sort of huge box, which is 3-dimensional. This is a 2-dimensional representation of it. But they don't move straight when there's a force, and the force is pulled between the 2. So if this is the earth, this is the moon. The earth is more heavy, so the moon moves more and is attracted by the earth, goes around. Okay. Now there are 2 problems in this picture. First one is how the hell the earth can affect the moon with nothing in between. I mean, how does the moon know that there is earth there? They're far away. How they can act on one another from a distance? And Newton was very aware of this difficulty of his own theory. He even called this idea repugnant, that 2 things could affect one another with nothing in between. But that's sort of the best he could do, and it's pretty good what he could do. The second question is, what is this thing he needed? Space. Space is a very Newtonian idea. Before Newton, people didn't think that there is a space in which things move. People thought that there were things, and space was the way they were one next to other. And in particular, they thought there's no empty space, because if between 2 things there's nothing, there's nothing. There's something, air in that case, and there's air. So what is this box in which things move all around us, which is space? That was what Newton left us with But the situation changed dramatically in the 19th century when Faraday and Maxwell, working out the electric forces, realized that there's another kid on the block, the field. There's another ingredient in the world, which is the electromagnetic field. And the electromagnetic field is something which is all over. This is my picture of the electromagnetic field, right? You know why it's yellow, right? Because light is a magnetic field also. And light is yellow, of course. So what is the point of the electromagnetic field? The point is that if you have some charge here and also attract another charge, but not directly, via the field somehow. The charge affects the field affects the charge, and the information that the charges here travel through the field. The field carries the information. And of course, Maxwell wrote the equations for the field, which is all around us. We're immersed in this field, the electric and magnetic field. Maxwell wrote these equations and did marvels. I mean, somehow all the modern technologies based on these equations. And he realized fantastic things. For instance, that this field can oscillate, can wave very rapidly, and these rapid waves are light. I mean, so he understood what light is. Plus, he understood that this field can also wave more slowly. And these are what we call today radio waves, which nobody had even suspected at the time that they existed. And this is the way, you know, my microphone communicates to the recorder, and we have all the modern communication. So that's fantastic, and that's how young Einstein learned the world is made of. Between Maxwell and Einstein, it's just a few decades. So it was very early after Maxwell that young Einstein came to the world. That's him at the age when he got his ideas about gravity, very young. So most of us here in this audience and speakers in this festival are much older than the age Einstein. In fact, most scientists did what they did. And Einstein understood that, well, if it's true for charges, it should also be true for gravity, right? So if two things attract one another, there should be a field in between, like the electromagnetic field. That's easy. So there should be a gravitational field. And Einstein was very convinced of that. He was realized that for Einstein, the Maxwell equations, the field, was something very real, even if it was so recent. His father, Einstein's father, was working doing power plants in northern Italy, and Einstein dropped school in Germany. He didn't like school. He spent 1 year in Italy doing nothing. Following his family, this is the power plant that Einstein's father was building in Pavia when Einstein went there. And of course, all this worked thanks to the Maxwell equation, okay? The rotors, the electric field, the magnetic field, and so on and so forth. So Einstein had a clear family presence of electromagnetic field, and he obviously understood that there should be a gravitational field. So when the Earth and the Moon attract one another, in between there should be a field, gravitational field. And here he gets his idea. And his idea is spectacular. Should we add another field, electric field plus gravitational field? Well, no. The field is already there and is Newton's space. Except that Newton's space is not rigid, it's not fixed as Einstein thought. So let me take away the rigidity. It's also movable, like the electromagnetic field. So that's Einstein's idea. Space, this Newtonian rigid thing, and the gravitational field, which carries the gravitational force from one particle to the other, from the Earth to the Moon, are the same thing. Space and the gravitational field are the same thing. So in other words, this field that brings the attraction from one side to the other is precisely space. More precisely, space-time. I'll come to that in a moment. This is what I was looking for. So here's a picture where the field itself, you see, it fills up everything. In fact, it is the space in which things move. He published this theory, the full theory of general relativity, with this idea worked up entirely in 1915. This is the paper, November 1915, with the full equations of gravitation. And beauty is that this entire idea is captured by essentially one equation which tells you how the field, which is space, react to matter and vice versa. And this is a single equation of general relativity written on a T-shirt, because I think that a good theory should be such that you can write the main equation, the fundamental equation of it on a T-shirt. So simple. So that's the equation of general relativity. I'm not going to enter into the details, but roughly T is matter and R is how the space curve. So everything comes out from that equation. An extraordinary set of marvels come out from this equation. One is that since space itself is curved, light doesn't go through because it doesn't go straight, because there's no straight in a curved space, or light bend. And as you know, bending of light was found very soon, a couple of years later. But I've cheated a little bit because, in fact, it's not space, it's space-time, which is curved. So when you think of this object here, which should represent space, it can bend and stretch and curve. This is actually space-time. So space at all different times is that bend. What does a bending of space-time mean? There is a simple way of thinking about that, which is the following. If you have a clock, a watch, the main idea about clocks is that they indicate the same time, right? So if you move around, come back, they indicate the same time, okay? But it is actually true that if these were precise enough watches, the following will happen. If I move one of them high and one of them low, I wait for a while, 1, 2, 3, 4, and then I bring them back together, I look at them. If these were precise enough, they would indicate different times. And this is not abstract or a consequence of a theory. This is something which is verified today in laboratories, a difference of altitude of few centimeters. Okay, 30, 40 centimeters is enough with a good clock. We do have good clocks to see that this indicates more time than this one when you bring them back together and you look at them. What does this mean? It means that time passes faster up here and slower up here, down here. So if you have a brother with your same age that live at the seaside and you go up in the mountain, you become old while he remain young. When you meet again, one is younger, one is older. This is a fact. Of course, the difference is very small on Earth, but it's definitely visible on with sufficiently good clocks, or it's an effect which becomes much stronger on, say, a planet or a star, which is much more heavy. And this is the reason, I throw this. Okay, why it doesn't go straight? Why it comes back? Since there's no force. Well, because look, for the same reason for which a airplane going from New York to Paris doesn't go straight on that map. It goes up north and then comes back. Why? Because to move from east to west is easier if you're north, because up north the distance between east to west is smaller than down. Earth is curved, right? So an airplane goes from New York to Paris straight, but in that map it does that. Exactly for the same reason, this goes from here to here straight, but it goes up because up time goes faster, so it's convenient time-wise to go from here to here going up. For those of you who have some knowledge of mathematics and Riemannian geometry, both the path of the airplane and the path of a ball that the two girls are throwing one another are geodesics in a curved space or curved space-time. So they both go straight in a curved space-time. Now, the curvature of space-time, as you know, can be so intense then it can make a hole in space-time, and these are the famous black holes, which when I studied at school were considered strange, mysterious, non-existing things in reality, strange solution of the theory which don't exist in reality. Today we see many of them. This is a astrophysical picture of some some black hole, and then all sort of other things which are the theory. You know, the space and time can oscillate, space itself can oscillate, it makes waves. These are the gravitational waves. This is a machine to observe gravitational wave. This is Virgo in Italy. There is another one in Germany. There are a couple of in the United States. And of course, space itself, since it can change shape, it can grow, and if you put it in the equations, you see that it cannot stay put. So the theory predicts that the universe can either expand or contract, and in fact it does. We have found evidence for that. So that's general relativity. So the key idea is that space is not something fixed, it's just a field, like the electromagnetic field. So the world is not made by space, time, and fields, but just made by fields and particles on top of one another somehow. Space and time are just aspects of a field. And that's what you should keep in mind about gravity in order to go to quantum gravity, and this concludes first chapter of this class. Chapter 2, quantum. So we've seen chapter 1, space and time are just aspects of a field. Now quantum. Again, just a couple of key ideas about quantum, which is what is needed to go to quantum space-time. Now quantum mechanics, So quantum mechanics came out from measurements, from observations in the around the turn of the century, to the 19th and the 20th century, and in particular the observation spectra of atoms. The light that comes from substances, from the atom emitting lights, is not at arbitrary frequencies, but on very specific frequencies that if you look for a spectrometer, if you just go through a prism, make some lines. So it was a long struggle to understand why these lines, why certain specific, why this funny specific frequency instead of arbitrary frequencies, which is what classical theory and the Maxwell equation would have suggested. And the guy who made the key step, the first person who wrote the equation of quantum theory is Werner Heisenberg, is him. And look, that's again at the age in which he got his step. It was around 25. That's when you get great ideas in science. So what is Heisenberg understood? What does Heisenberg understand? Well, in his own words, he tells the story of his understanding of quantum theory, the key insight of quantum theory. He says he was in Copenhagen. He was visiting Bohr Center, which became the key place for modern physics for quantum theory. Of course, at the time, it was just a small group of people who was heretical with respect to everybody else, right? Because that's the way science works. Very often, the ones who later celebrate are the great people, a small community, which does something completely different than everybody else. So Heisenberg tells the story that he was thinking about everything, and he was one night going out in the park, and very dark. This is Europe 1925, and the park was dark. There was just some lamps, some spot of lights here and there, and at some point he sees a man under one spot of light. Okay, and then the man disappears. No man there. And then he sees him appearing in another spot of light. And then again, disappears, he appears, disappears, he appears. Okay, and then disappears. And then he thinks, Heisenberg, and says, well, of course, I don't see him, but he's somewhere in between. Obviously, a man is something, you know, big and heavy, and he's not going to disappear and reappear. It's just... And then he has a flash. Yeah, that's for a man. Well, what about an electron? When I see an electron here and an electron there, am I really sure? An electron is not big and heavy like a man. Am I really sure that he's all the way in between? And he realizes, so this is the question. What about an electron? If I see an electron here and I see an electron here, or a small object, a radiation of a nuclear decay. I have a nucleus, there's an alpha particle inside, I have a Geiger counter here, it clicks, so it was here, it was here. What about in between? And here's the insight that everything starts making sense, or more sense, if we just don't assume that something existed in between. That's his Heisenberg insight into quantum theory. That's his huge jump, leap into sort of modern physics. So this is his idea. First of all, reality is discrete. The electron is here, pip, then is here, pip, then something else, pip. This is a way of putting it. God, if he existed, if she existed, did not draw the world with a continuous line, but just dotted it. Right? The world is less dense than what we think classically. Second, between one dot and the other, there is no strong deterministic law that says when is the next dot going to happen. There are only probabilities for one thing or the other to happen. You know, quantum mechanics give up probability. And finally, reality is relational in the sense that when is it that an electron exists next time? Well, this is all the alpha particles in the nucleus, then the Geiger counter clicks. What is it that determines this moment? When during interactions, the alpha particle interacts with the Geiger counter. So things happen at interaction, and they happen sort of with respect to the system, to the physical system they're interacting with. This is the core of quantum theory. Of all these things, perhaps the most important is the first one, is discreteness. Quantum theory is the realization that there's sort of less stuff in the world than what classical theory says. World is discrete. And one way of viewing this is applying quantum theory to the electromagnetic field itself. Okay, so this is a classical, Maxwell gave us a classical description of the electromagnetic field, which is a continuous thing moving space-time waves. But quantum theory shows that there's a discreteness inside. It's the same kind of discreteness as the spectra of the atoms. And what is discreteness? Photons, particles of light. Looking into small electromagnetic field, the light that we see is in reality, interact with us. It's better to think about it as a cloud of small grains, which are the photons. So this discreteness is the core of quantum theory, okay? And this profound discreteness of nature is the same discreteness that gives the photons, gives the spectra of the atoms, and is also the discreteness of matter, right? Matter is made by atoms, which is made by elementary particles. What are the elementary particles? Are the same things as photons, quanta of a field. And of course, the idea that the world is discrete goes back to ancient thinkers, and Democritus is the great physicist or the great scientist, the great philosopher of antiquity, who insisted, and he actually promoted the idea that the world is atomic, the world is made by atoms. So that's my summary of quantum theory, quantum field theory. These fields, which make up the world, remember, they are made by grains, by quanta. And these quanta are the photons, the electrons, the quarks, the things which are the stuff of the world. The quanta of the fields are particles, grains. And this concludes second chapter, quantum theory. So we've seen generativity, we've seen quantum theory. Now we go to the third chapter, which is finally quantum gravity. So third chapter, quantum gravity. Gravity, space and time are aspects of a field. Quantum field is made by quanta. Electromagnetic field is made by photons. We'll bring the two together. It's not very complicated. The two together imply that in some sense, space itself, or space-time itself, is discrete, is made by quanta, the quanta of space. Where are we going to see this quanta of space? Well, first of all, let me be clear here. We know a lot about the world because generativity functions extraordinarily well. We know a lot of the world because quantum mechanics function extraordinarily well. If we believe these theories, what do they say together about reality? That's a game, which is the game of quantum gravity. So generativity, quantum theory, what do they imply together? Whatever they imply together is quantum gravity. That's what quantum gravity is. Of course, we need to vision and understanding equations, and then testing these equations to see if this is the vision is right, the equations are right. So where is quantum gravity becoming relevant? Well, again, this is an electromagnetic field. In the small, there are photons. This is space-time. Let's think about space for the moment, then we'll go about time. In the small, there should be the quanta of gravity. So quantum gravity is, first, about what happens at a very, very small scale. A very small scale means if you look at this and you do smaller, 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 you see some structure. Okay? This is another picture of it. And in fact, it's not difficult to from what we know from quantum mechanics and general relativity, look at the scale where this is expected to happen is a scale of 10 to the minus 33 centimeters. It's a very, very small scale. At this very small scale, there's some structure. In fact, there's also some structure, right? There's some threads that makes it. Nature rhymes with itself, like Ed Witten was saying yesterday in his lectures. Space is not a continuous. It moves, is a field, but it's not a continuous as a structure. The structure is granular. These grains are what makes the quantum aspect of space. So let me repeat the logic here. Space-time is a gravitational field. It's the same thing. So space-time is a field. Fields are made by grains. Electromagnetic fields made by photons. Space itself is made by grains. These are the quanta of space. This is a artistic picture, movie, sort of giving an intuition about this very, very short structure of space-time, where there are individual things, which here represent as a triangle, tetrahedra. But the important point is that these quanta, this grain of space, are not immersed in a space, like sort of one sees here. They are space themselves, right? So they are not like photons, which live on space, because they live on the gravitational field, they interact with the gravitational field. These are themselves the space. So space is made by individual grains, and the theory that we have to write is the mathematical description of this grain. Now, these grains, of course, know when they are next to one another. So if we describe the fact of being adjacent to one another by a little line, like in this picture here, we get a graph, and we get a description of space in which a lot of little lines intersecting to one another. And this is a picture. This is an image, sort of something I did many years ago, trying to give an intuition about the small-scale structure of space. I was in my hometown in Verona, in Italy, and I basically bought all the key rings I could find in the city, going from hardware store to hardware store. There were no key rings in Verona for several weeks after that. And the idea is that, you see, it's a sort of chain mail. And if you follow along this graph here, if you make a circle, make a little loop. So this is what sort of holds space together. So you can think space at a short scale, little loops. This is where the name loop quantum gravity comes from. It's a quantum theory of gravity which describe all these individual quanta of space attached to one another, and the lines of being attached, you can think as little individual loops going around. This is the same. This is again a picture of the same thing. This is the relation between the chunk of space and the graph describing them. This graph have a name. They're called a spin network. Network because it's a network of things, and spin because in the mathematics of the theory, there are spins, little half-integer numbers, which are the quantum numbers associated with the geometry of this chunk of space. Roughly, when two chunks of space are adjacent to one another, there's a surface in between. Surface as an area can be smaller or larger, and because it's quantum mechanics, this area cannot be anything, has just some spectral value, like the spectra of the atoms, and which are given by those spins. Now this is space. Okay, this is a picture, an intuitive picture of space, but we want an intuitive picture of space-time. So what is an intuitive picture of space-time? Is this evolving? So this is a part of the net, one grain of space, 3 grains of space, that they can merge into one, and they can expand in 2, and you can represent it. You see this yellow line, it sweeps a surface, so you can represent it as something which in the technical language of the theory is called a spin foam. Spin foam again because there are spins there. Why foam? Because you see this is like a foam. This is bubbles making a foam. Little surfaces joining, and little edges in turn joining in vertices. And you should think of this as a microstructure of space-time, where, again, the surfaces, the lines, are not immersed in space, but are themselves what they make space. And this if you know some physics and you know Feynman graph, it's like a version of Feynman graphs for space-time itself. What is Feynman graph? Feynman graph is a description of this, right, of a field in terms of its elementary quanta interacting with one another. So this is a photon, which becomes to an electron and anti-electron, and other photons, and so on. So an electromagnetic field in space-time interacting with a Dirac field can be represented by a set of Feynman graphs, which are the individual quantum interactions between the quanta. A spin-foam is the same for space-time itself, which is nothing else than a gravitational field. The difference is that a Feynman graph is immersed in space-time. This is space-time itself. Now, what the good of the Feynman graph is not that it's a nice picture, is that there is some math associated to it. There are some rules for computing a number out of it. And these numbers allows us to predict what happened in the future, the probability of what happened in the future, if we know what happened in the past. And the same is true for spin foams. There's some numbers associated to it. There's a calculation rules. And so there are some equations in the theory, and I told you that you shouldn't believe a theory unless there's a simple set of equations that you can write on a T-shirt. And this is a T-shirt, and these are the equations of loop quantum gravity, which give a way of computing how the individual quanta of space evolve through space-time in a discrete manner, and how things, happen. This is very good. So now we have a quantum theory of gravity. That's summary so far. Space and time are just aspect of a field. The quanta of a field are the particle. Space is granular. We have equations to see how it evolves. So far, so good. The question is that true or not? And that will be the next chapter, the last chapter. Can we test this? Good. So last chapter, how to test this theory of quantum gravity. Again, first, gravity is just space is a field. Second, quantum theory, fields are granular. Quantum gravity is description of the grain, the quanta that make up space. Okay, we have equations. Can we check this theory? And this is the last chapter, fourth chapter, about white holes. Now, why white holes? Quantum gravity is relevant if you look at the very, very small, but we don't have machines for looking at the very, very small. Okay, the LHC can see at a scale which is small, but is hugely bigger than the actual scale of the quanta of gravity. So it doesn't help here. Quantum gravity is relevant when nature itself does something in the very, very small and then gets amplified. And there are two cases that we know well where this is relevant. One is the early universe. There's a lot of people who study the early universe trying to use the equation of loop quantum gravity, compute predictions, and seeing the CMB, in the cosmic background radiation, if we can see effects of quantum gravity effect at the beginning of the universe. This is a lot of work in that direction. But I want to tell you about the other possibility, which is black holes. Black holes, we have seen they exist. When I was a student at university, they told me, well, they are just solutions, but they don't exist in reality. That's what my professor told me at the university. Never believe the professors tell you at the university. They were wrong. Black holes do exist. In fact, my book said that. Book by Steven Weinberg, you can still look at it. Written in the 70s. In the chapter, it's a great book, fantastic book on general relativity. In the chapter on black holes, it says, well, there are these solutions, but it's very unlikely that they exist in the universe. Wrong. Okay? Great scientist, one of the greatest living scientists we have, was wrong. Now today, in fact, we know there are other solutions of general relativity, which is white holes. I'll say in a moment what they are. And if you typically look in a book of general relativity, they say, well, these probably don't exist in the universe. So maybe they do exist. Why white holes are relevant for that? Well, this is an actual black hole in the sky. This, remember, is a picture of the geometry of the gravitational field around it. Usually when we see black holes, typically they're not alone because they're black. So what we see is when there's a star near to them, galaxies are full of binary things, 2 stars, 2 neutron stars, 1 black hole, and 1 stars. So if you have 1 black hole and stars, the black hole is very attractive, and typically the star loses material which falls into the black hole. So we see things falling into the black hole, and it radiates a lot, and that's what we actually see. The jet here is because, for reasons which are not totally clear, the matter that spiral toward the black hole, part of it falls inside, part of it is emitted in the north and south pole. We see a beautiful picture in the sky of these jets here. So a lot of matter falls into the black hole. Falls. Okay? The black holes itself, most black holes we see are formed by stars which collapse. So a lot of matter, you know, atoms, nuclei, protons, fall into the black hole. Fall. What happened to the matter that falls into the black hole? I go to the center, and the present answer is that we have no idea. So we know very well what a black hole is. We know very well the surface of black hole will happen. We know the geometry inside. We know the fields. We know how matter moves inside. We know that everything gets to the center. And in the center, we have no idea. Why we have no idea? Because if you use general relativity, the equations lose making sense. Everything becomes infinite. It's what is called singularity. The thing doesn't make sense at all. But nature is and happens. So something is going to happen there. And things fall into a black hole. And what could happen? Well, the reason we don't know, of course, is because there quantum mechanics become important. So you need a quantum theory of gravity. And what is a quantum theory of gravity likely telling you? Well, you know, everything becomes very small. And then there's a quantum phenomena. A quantum mechanics allows things which are forbidden classically. Typically, for instance, take a nucleus. Uranium nucleus is an alpha particle inside, and classically could never get out, but it does get out, and that's radioactivity. Classically, an Arrhenius nucleus is sort of stable, more or less, in some approximation. Quantum mechanics is not. Classically, a black hole is stable, it's going to stay there forever. Quantum mechanically, not. So here is what it's likely to happen. This is a black hole. Matter falls inside, gets to very small, and then explodes. And the intermediate, so matter falls in, compress horrendously, become very small, we call it a Planck star, the stage where matter is maximally squeezed. Then quantum mechanics come in, it does the same thing it does on atoms, it does the same thing it does on nuclei. Quantum mechanics produces a sort of repulsive force, and everything gets compressed and then bounces out. Bounces out and makes what? Well, the same thing that, you know, if you take a ball, I didn't bring a ball, but you can visualize it. You let it go, it goes down, it compresses, and then what? Then it bounces up, right? So the bouncing up is the same as going down, but time reversed. So what is the time reversed of a black hole? It's a white hole. Black hole, everything can come in. White hole, everything goes out. So the most likely thing that happens is that black hole forms, quantum gravity, white hole. Wait a minute. It doesn't work, because you would say immediately, because this is going to be fast, right? Boom, boom. But we see a black hole in the sky staying there for long. Aha. Remember the guys, one up and one down. Short time for this, long time for that. If you compute the time that passes, that lapses, inside the black hole, imagine you sit on the star, you see this explosion. For you, it's, say, 1 millisecond for a star. Now, your brother is outside the star, watches that. It doesn't have to be the same time. It's much longer, for the same reason for which the mountain is much longer. Except that now, the difference of gravity, gravitational potential, inside the black hole and outside is huge, much, much bigger than between sea level and mountain level. So the person who is outside and he watches all that has the time to become very old, and in fact 1 millisecond inside can correspond to 10 billion years outside for a stellar black hole. So here's a picture of a black hole. Star collapses, boom, boom, explodes immediately. But because of time dilation, if I look at it from the outside, I see it as slow motion. So I see boom, 10 billion years, I'm not going to wait, and that's what a black hole we see in the sky is. It's a collapse, it's a bouncing star seeing in slow motion, very, very slow motion. Now, do we have a chance to see anything like that? Well, remember that the universe exploded in a big bang. So long, long ago, everything was very hot and compressed. So this is expanding universe. We are here. We have so late in time, 10 billion years or 15, whatever, 14 billion years from the Big Bang. We have our radio telescope. Imagine that long, long ago, when the universe was small, a black hole formed. Why? Well, because it's very hot. Everything happens, and then it's likely that it's possible. We're not sure. We don't know that matter collapsed in the strong fluctuations of density and everything at the time. So a black hole forms there. The matter falls in, immediately bounces out, but in the meanwhile, outside, a lot of time has lapsed. Okay? So when it actually, the white hole actually explodes, is now. And when it explodes, it's going to make a boom, like everything which explodes, so it makes a signal that we might see it. So here's the idea. Maybe we can see today some signals that came from black hole which collapsed the early universe and are exploding today. Now, recently, a small group of people have computed the aspect of these signals and came out with a certain wavelength, and it turns out that this wavelength is very similar to things which actually have been observed, which are called fast radio bursts, not long ago by radio telescopes. So it's in the radio. This is a signal, and it's a very short burst. It's more or less the right wavelength. And the question is, are these signals which have been observed produced by the white hole exploding that were formed in the early universe? The answer to this question is we don't know. Okay? This is not something which has been confirmed. This is not something which is certain. This is not something, but is an attempt to see an effect which is a generally quantum mechanical effect, because the bouncing of the hole is a generally quantum mechanical effect, which we could see together today, and which could tell us something about the quantum property of gravity, and which could confirm or disconfirm the set of basic equations of loop quantum gravity, which I showed you, or tell us something directly about quantum gravity. Until we don't have observation of this kind, now this might work or might not work. It might turn out that this fast radio burst or something else, completely unrelated. It may turn out that there are not enough black holes in the early universe to see them today. Or it may turn out that's what it is. And then we would say, yeah, great, we got it. Okay? So this is the situation today. Let me just summarize the story here. 4 chapters. First one, I gave you a sort of 10-minute versions of general relativity. The core of general relativity is understanding that there is a gravitational field, there's space-time, the two things are actually the same. So space-time is just a field. The universe is not made by space, time, matter. The universe is made by fields, and these fields have features that allow them on the large scale to describe them as space, as time, as matter, as protons, as photons, as night sky, as people, as you and us talking, smiling young kids, everything. Fields. Second, fields have discrete aspects. This is what core of quantum theory, a probabilistic aspect, relational aspect, but discrete aspect. So they're made by quanta. There's no infinity in the world. You cannot go infinitely small, you cannot go infinitely large. The discreteness. And these quanta, the photons for the electromagnetic field, are the quanta of gravity, the atoms of gravity, the grains of space which make up a gravitational field in their space. There is a theory for describing that, which is loop quantum gravity, which is written in terms of spin networks, which are the states, which gives the short scale description of this grain of space that touch one another in spin forms. ways of computing the way these evolve. Okay, and I've just flashed the equations of spin forms. It's like Feynman diagrams, but not for particles, for quantum space themselves. And finally, in the last chapter, I've told you that the effort now is to try to see whether these equations describe the world or not. And to do that, so they're right or wrong, to do that, one has to look for observable consequences. I illustrated one of the tracks that we're following, hope, maybe a small hope, but I hope that perhaps the quantum gravitational bounce of a black hole into a white hole could be observable, and even perhaps could have been already observed. Thank you.